Welcome everybody. Today we have a pretty special video because I'm joined here with Tom from Tom Rock's Math YouTube channel. Hello Tom, how are you doing?
I'm very good, Trevor. Super excited to be a guest on your channel, actually.
Excellent.
It's a channel I've been watching for a while, so you know.
Oh, I'm so glad.
This is big.
Well, Tom has an excellent channel as well, so you should definitely go check out his videos. And specifically, we just got done filming a video talking about fluid mechanics. Well, Tom taught me a little bit of fluid mechanics. This is not a field I know well. It was a ton of fun, so I definitely encourage you to check out that video. But here on this channel, we're going to be talking about some algebraic topology. So I have two basic goals. I want to give a little bit of a loose sense of like, what do these words mean? Like, what does it mean to be an algebraic topologist? What is algebraic topology? And specifically, we're going to focus on one type of algebraic topology, something called the fundamental group. So that's the plan.
I understand the words. I certainly know the topic. I have never studied algebraic topology, so I've never studied topology. So it was one of the optional options during my degree, and I never felt very comfortable with the abstract nature of the topic.
That's right.
I'm very excited to potentially learn topology for literally the first ever time.
That's interesting. It is one of those subjects that some people like, they dive into it, it's kind of like the cool, sexy side, and people are really interested in that, or people are like, no, I never want to do this.
Yeah.
So maybe I would start by just trying to get a bit of a sense of what the two words mean. So, I mean, algebraic is probably one we're all familiar with, but I'm curious to hear your thoughts, Tom. Like, what kind of connotations come up when you hear something's being described as algebraic? What does that mean to you?
I would say you can express it with equations.
Mm-hmm.
So in some sense, I often think of this as how the geometry course that I actually teach here at Oxford to the first years. And the way I describe it to them is we take all of the geometry you've done at school, triangle theorems, circle theorems, drawing nice pictures, and we express those as equations using vectors.
Okay.
So I often think of that as like, I know it's not algebraic geometry, but I often say to them it's kind of taking your pictures and turning them into equations because that allows you to generalize the higher dimensions.
That's really nice, yeah. And I like that there's sort of that, when you have something described algebraically, there's sort of a concreteness to it. You have equations, things happen, like 1 + 1 = 2. It's very concrete and sort of written down. Okay, so that's maybe the spirit of the algebraic word. What about the spirit of the topology word? Well, okay, so you teach geometry, and in geometry we care about shapes, but with a certain rigidity to it, as in we care about distances and angles, and things are sort of quite fixed. So we're going to talk about topology, which also cares about shapes. But I sometimes joke, I've stolen here my 3-year-old's Play-Doh. It's like geometry, but it's sort of Play-Doh. I can squish it around and stretch it out and move it. And there's a classic joke in topology, which is that a little donut, kind of like this one, which is sort of something that has a single hole, is in some sense the same thing as this coffee cup, which also has just a single hole here. So we're sort of stretching things around, and that's what we're going to try to do. So when I say I'm an algebraic topologist, okay, you've got the one thing which is all wishy-washy and stretchy and moving around, and then you're trying to impose on it the rigidity and the concreteness of some sort of algebraic structure. So how can we possibly manage to try and do this? Okay, so I've started by writing down just a few different letters just to build a bit of intuition for the kind of changes, the kind of ways that we can manipulate. So what I want to imagine is that all of these letters are made out of Play-Doh, and I can sort of move them around, but there's a few restrictions, okay? I can't rip anything, like I can't break it apart, and I also can't just smush it all together, like just blast it all down into a single ball. Like, if there was a hole there, you've got to preserve the hole. So I'm curious, Tom, do any of these letters see, from the perspective of a topologist, to be the same thing, or some of them different? Which of them are the same? Which of them are different? What do you think?
So from what you've just mentioned, I'm picturing here, I'm not allowed to add or remove holes, but within reason, anything else is kind of possible.
That's right.
Like, okay, so then I'm going to start by looking at holes. So
Okay.
A has one hole.
Yeah, if I draw it
say
properly, it's
A-
got a hole.
Yes, A has a single hole inside the triangle, and so does D. So I would guess that A and D would be topologically the same.
Okay, I agree with you. And maybe to sort of illustrate the idea, the kind of things I'm allowed is like, for example, in the A, maybe I could shrink these little tails and
Yeah.
be like, it turns into a triangle, and then a triangle could sort of be turned out into a circle, and sort of the same thing with D.
Yeah, exactly.
Okay, so those
yeah.
are two similar ones. What about any other similar ones?
B has two holes, and it's the only one with two holes, so I would imagine that is in its own
Yep.
separate little group.
I agree. Maybe we'll
and
call
then-
this one, I'll put a hole and then a circle and then another circle. Kind of looks like an 8. That'd be the same thing.
Yeah. And then C, E, F, and G all have 0 holes, and so I guess all of those could be turned into like one line.
Exactly.
Like a
Or
form, another
even take
single-
the line and collapse it all the way down to a point. That'd be perfectly fine.
Yes.
And I think that's it. If I go through the rest of the letters, I think that there's none with 3 holes in it. I think B's the only one with 2 holes. So really, when you think about the letters, there's only 3 letters. There's a point, there's a circle, and there's 2 circles. Those are the only types of letters that exist in the topologist's alphabet. Okay, now, when we do this type of manipulations, sometimes we do lose some things, like we lose the distinction between E and F when we think of moving them this way, but I want to show you a different spot where we could lose some information. So, okay, I have a little rectangle, and if I fold the rectangle around and sort of imagine gluing it, it forms a cylinder.
Yeah.
Right, so I began with my rectangle and I turn it around and I have a cylinder. Okay, this is one thing I could do. And what I could do differently, this is the classic Mobius strip, is instead of taking it and gluing it this way, I could introduce one twist to it when I grew it, and it would look something like this. I'll try to hold it up here for the camera. Now, these seem like different shapes, but from the loose rules that I've described, in effect, they're actually exactly the same. And I'll try to describe why, so you're not going to be able to see it, but give me just a moment to draw a line. Okay. So if I imagine drawing a line in the center of my strip, I could sort of say, well, look, this thick two-dimensional strip, I could collapse it down at all points and it would just become the circle. But this is true for both the cylinder and for the Mobius strip. You can always just sort of collapse it down to this line. And indeed, if I put it together and glue it in the way that is, makes sense for the Mobius strip, this object, which is bizarre in that it only has one side, even though it came from 2 pieces of paper, it's very meaningfully different from the cylinder. If you think about the type of equivalence we're talking about, well, it's just take everything down and put it down into the circle, and so this theory can't tell the difference between a cylinder and a Mobius strip. Okay, so that was just some of my preliminaries, just to get a sense of the kind of operations we're going to do. Let's try to do a slightly trickier one. And for this one, we're going to try to figure out a way to associate an actual algebra to it. Something where we're doing counting or adding or subtracting. That's the kind of notion we want to build up to. What I want to imagine is that I begin with a ring like this. And I want to imagine all of the space that is not that ring. So if you imagine it living sort of in 3 dimensions, what is the complement of that space? So perhaps if I take a little string here, I'm asking what is all of the other space? That's what I'm trying to visualize here. Okay, and this is what I'm going to do. I'm going to draw loops in the complement of that one ring that I've written down. I'm going to draw loops in all this other space. So here's an example of a loop I could draw. Maybe I'll start here, I'll go in, and I'll leave a little gap and come around like this. This little space was just meant to denote that it was going underneath the blue one. That's all. If it's solid, it goes over. If it's got a little space, it means it goes under. So do you sort of see what I'm trying to say here with a loop going through the complement of the blue loop? Maybe I'll call this one A and this one B. Okay?
Yeah, it's almost like 2 chain links, I'm thinking in my head, picturing 2 links of a chain.
That's exactly right. Now, I'm going to associate this with the number 1 for a moment. We're going to come back and think about other numbers, but just vaguely, let's just think about this as number 1. I'm going to tell you the number 2, okay? Yeah. So the number 2 is almost the exact same thing, but it does the following. It loops around, then it loops around a second time, and comes back here. This one which has two loops I will associate in some vague sense with the number 2. So hopefully you're visualizing the same way as I am, sort of like double looping before I come around. 3 would be a triple looping, 4 would be a quadruple looping, and so forth.
Yes.
Now, I should maybe also specify that because we're thinking with our topologist hat on, the exact shape of this doesn't matter. Like, if the loop went through and then, like, went around over here, that would still be a 2, because that would sort of just playdohing the loop. Okay?
Yeah.
What do you think 0 is?
Something that doesn't intersect the blue, or the blue by itself, perhaps.
Exactly. So maybe just something like that could be associated with 0. There's no interlocking. Yeah. Okay, so that one's reasonable. What about -1 then?
Okay, so if we're looking at intersections, that's not intersecting, so if there's a negative intersection, is -1 if it's fully contained in A? Like inside?
Oh, I see.
So
okay,
like that one.
So I'm imagining loops that have this requirement that they can only exist in the complement of A. So I liked where you were thinking about it. But perhaps I'll draw the original one again, which I sort of did with a specific choice of orientation where I'm going over first and then I'm going under, and maybe I'll indicate it that really what I was doing was putting an arrow to tell you which way I was doing this. Okay, so then -1, now I can see you already get it, is if I draw just the other way. That will be associated with my -1, okay?
Yeah.
So I've given you a bunch of shapes, and I think we have an intuitive sense of what it would mean for them to be associated with numbers, but now I want to add stuff. Like I want to do things like 1 + 1 = 2. Okay, so that's the sense that I have. So if I'm going to do that, let me draw a 1. Okay, that's a 1. Yep. We're always going to start down here, and I'll call it x0. I'll just call it a base point. We're always going to begin at the same spot. And then I'm going to draw another 1. So my other one's going to go a little bit like this. Maybe comes over here, and I've got a 1 sticking out like that. So that's a 1. That's a 1, and I want to be able to say 1 + 1 = 2. So
yeah.
Can you visualize how I could perceive this 1 + 1 = 2 in this context?
I'm thinking you start at x0 with the red, the first one you drew in red.
Yeah.
Then you go around all the way back to x0, but then you continue on the white one.
That's right. So you're really saying, look, I'm going to do the one loop, and then I'm going to do the other loop, and collectively I think of that as just one loop that's now wrapped around it twice.
Yeah.
And what I could do here, let me try to change the exact type of eraser that I have here, is I could sort of imagine it a little bit like this. It comes around, and then it never quite goes back all the way to x0.
Yeah.
There's that, like, because it's in the middle of the loop, it doesn't have to go right. You could very, slightly move it away, and then that sure does look a lot like the 2, and I think we can say 1 + 1 = 2 in some sort of non-trivial sense here.
Yes.
All right. Okay, what about, let me ask you one more. What about 1 - 1 = 0? How would you visualize that?
If you were to start at x0 and draw your red loop, you'd get back to the beginning, and then you would sort of completely reverse direction and go backwards.
That's right. So maybe we'll start over here, we'll come back, then we go in reverse, come back. And I don't know if you can sort of visualize it. I can almost imagine just pulling on that and the whole thing would just sort of slide out of the... Like, there is no knots there, right?
I was about to say, because they're not touching, because the way you've drawn it, they're not quite touching at that point. You can actually see how you could be able to, you could like pull the whole thing out. It's not actually
exactly.
And it's not linked like a chain anymore. Yeah.
Exactly. Okay, so that one, I got to keep on changing my titles here, is 1 - 1 = 0. Okay, so we've been talking about it vaguely, but what we're going to try to make more precise now is the notion of a homotopy equivalence. And a homotopy equivalence is going to be trying to take different paths and say that in some sense they're the same path. You can't really tell the difference between them. So I've talked primarily about loops, but just for the definition, I'm going to actually introduce it by imagining some path that goes between two different points, say x0 and x1, and maybe I'll call this particular path f0, okay?
Yep.
And then I can imagine that there's some other path that also goes between x0 and x1, and this path I will call f1. So two different paths, and I want to argue that they're sort of the same. And the way I'm basically going to do this is say, well, look, I can imagine a whole bunch of sort of like intermediate paths that sort of go in between them, that sort of take the f0 and manipulate it down to being the f1.
Yeah.
So really what I have is I have a family of paths, which I'll call f sub t, so one for every t, where t is between 0 and 1 here. And this family of paths always takes an interval, the interval from 0 to 1, and it tells you, well, how do you put this in whatever the space is? Your space is going to be denoted by capital X here. So f0 is indicating the top path that sort of went along the top, f1 the bottom path, and then ft would be like this family of ones that was all in the middle of it. And there maybe would be just a couple of properties that would be associated to this, like for example, if I was going to take f of t at 0, like if you were going to always plug in like the left endpoint, then this is going to have to just, well, what do you think ft of 0 should always be?
Your starting point, I would guess, so maybe x0.
So x0 and similarly ft of 1 is just always going to be the endpoint. And then finally, maybe I won't write it down, but there's a continuity condition here that this has to be continuous, which is the real way that we sort of codify. You can't break it up or have asymptotes or any of this nonsense. We're gonna demand there's a sort of a continuity property here. So I've told you that we're trying to build to something called the fundamental group. And the fundamental group is going to be this object that allows us to study different topological spaces. And so a few things are needed. The first is that if I look at this f0 and this f1, the language I'm going to use is I'm going to say that there's a homotopy equivalence between these two things. And as mathematicians, when we try to talk about a notion of equality in a particular sense, what's our sort of terminology for a generalized notion of equality?
That they are equivalent, that they are equal, they are
sure, and sometimes more precisely we'll say that there's an equivalence relation.
I see. Yes.
Right, which I was leading you in a bad direction. And by the way, I have a video on equivalence relation. I'll link it around for anybody who's not interested. But basically, we say something is equivalent if it has a bunch of different properties. A sort of reflexivity property, like f0 is homotopic to itself. A symmetric property, like f0 is symmetric to f1, means f1 can come back to f0, and a sort of a transitivity, like if f0 is homotopic to f1 and f1 to f2, then f0 goes all the way to f2. So any relation that has those three properties is called an equivalence relation, and we could prove it, we're not going to, but this has that particular property, and so it is a real sense of equality, or more broadly, we call it an equivalence relation. Mm-hmm. Now, I need to say more because I've indicated that we're going to talk about the fundamental group. And if anyone doesn't know what a group is some set of objects that also allows you to do something like addition or multiplication on them. So I had to figure out, how do I add things like this? Or perhaps how do I multiply? It's going to be a new concept. Doesn't matter which of those two words we choose to apply to it. So, in other words, if I was to, let's do the version where x0 and x1 are the same, so we've got a loop. So we've got some loop over here, I'll call this loop f0, a second loop over here, I'll call this loop f1. And if I'm interested, actually, you know what, I'm going to change my nomenclature here, I don't like it. I'm going to call these, what do I want to do? I will call this f, and I will call this one g. Just to keep, I'm not trying to make a homotopy between these two things. I'm just saying I got two different loops. So what I would like to do is to create a new loop out of these two existing loops. I will call the loop f multiplied by g. This is maybe the product of f and g in some sense. And you actually gave me the hint of how I should do this earlier. Do you remember how we added or multiplied two loops previously? What was our trick?
We did one, got back to the beginning, and then went round the other one as well.
Okay, right. So our idea of the new loop is we go around f, then we go around g.
Yeah.
And if we add in that constraint that we want to think of this as a path that goes from the interval 0 to 1 into our space, how would I adjust for the fact that it needs to be on the interval 0, 1 every single time?
How would you adjust? Would you like divide through by f plus g? Divide through by like the total?
Okay, I see where you're going.
Some kind of...
So what I guess I'm imagining is if in the first 0 to 1 you did f, it would take a whole second 0 to 1 to do g, but then that would give me a loop that was going from 0 to 2, and I want sort of definitionally all of my loops to be 0 to 1.
So you just divide by the total number of loops you've done, so 2 in this instance.
Exactly. And basically I'm thinking I'm going to go twice as fast for twice as long. So perhaps I could define this in a sort of a piecewise way. So I'm going to go on f, not from 0 to 1, I'm going to go f from 0 to 1/2. And so what I will do is f of twice s, so going twice as fast for, well, half as long. So we'll end at 1/2. And then g will be twice as fast as well. Okay, so what should I do here? So it's going to be also a 2s, but I got to shift a little bit. What do I have to do? I guess a 2s minus 1 if I'm going to be starting at 1/2 and going all the way up to 1.
Yeah.
Something like that. So the idea here is I now have an operation on loops. You have a loop that starts at a base point, and I have a loop. You and I can, let's call it the product. We can put them as a product together. Just kind of like how if you have different numbers, you can add them together. And this operation has all the normal rules that you think would apply, like an associativity property. Like f times g times h is like f times g times h. So all of the rules that are formally part of the definition of a group, this we could prove, we're not going to do it, but we could prove it obeys all of those things. Okay, so here's our opportunity to actually write down a definition. We will call the fundamental group. And we need a definition or a symbol for it, and I'm going to call it pi, because pi is cool. Pi 1.
And it's on your t-shirt.
Oh, that's true. Exactly. We'll call it pi 1 for here. This is the actual standard choice. This is called the fundamental group, or the first fundamental group. We're not going to worry about beyond the first, but the first fundamental group of some space x and starting from x naught. And it just refers to that equivalence class of paths starting at x naught in the space x.
Yeah.
Okay. And my claim here is that this really does form a group. We have a bunch of objects. There are all these different equivalence classes of paths. You can add your objects together according to this operation. All of the axioms of a group are satisfied, and so you can go and manipulate stuff. And now that we have this, we can do, for example, if you have a space, and I have a space, and we're not sure whether your space and my space are the same space or not, but if you have a different fundamental group than I do, our spaces have to be different.
Yeah.
So that's our sort of big takeaway. Okay, so let me try, now I'm going to put you to work if you don't mind.
By all means.
I know you've been standing there patiently, now you get to use your chalkboard for a moment. Okay, so I'm going to assign you to compute the fundamental group of a few spaces. You have a blackboard behind you, which is kind of like R2. So perhaps the first thing we could do is to compute the fundamental group of R2. So, well, why don't you draw a loop somewhere, doesn't matter, any loop you like.
Okay.
Yeah, that can be our base part, and that's going to be a loop. Okay. So, you could probably draw another loop that was homotopy equivalent to that loop. It would just look pretty similar, right?
Yep. So, if I just went like that.
Yeah, okay. Can you draw a loop that's not homotopy equivalent to the one you've drawn?
I don't think I can. Unless, the only thing I'm slightly worried about is if I were to, for example, draw it over here, if I were to draw something that maybe like crossed itself, would that be allowed?
So that actually is allowed. Our only restriction in our definition is what happens to the endpoints, and otherwise it's continuous. So infinite crossings is perfectly fine. Okay.
So in that case, I don't think I can draw anything different. I think I need that hole. I need that hole that we were interlinking things with earlier.
All right. So I agree with you. I also can't think of one. And so could we be confident saying that the fundamental group of R2 was just equal to 0? There's one thing, that's the one loop that you draw that you could just contract it right down to your point. It's just sort of the constant loop that stays at the point. That'd be another one. Anything else that you draw is the exact same as that. So there's one object 0. We'll call that the group that's just the 0 group.
I agree with that, yes.
Okay, so why don't we erase that one? I'll make you do another one. Okay, so now we're going to do it slightly more complicated. And I'm going to do the fundamental group of S2. In other words, the two-dimensional sphere. So why don't you try and draw a two-dimensional sphere if you can on the board?
A two-dimensional sphere. Does that just mean a circle then?
Ah, good point. No, I mean something that is... It lives in 3 dimensions, like the surface of the Earth, like my orange that I have here.
I see.
And so I sometimes draw an equator on it to make it look a little more 3D-like. You're drawing it in 2D, but I want to imagine a two-dimensional surface is what my sphere S2 is called. Beautiful.
Yes, okay, so I see. So this is like, I like your way of saying, so this is like my round Earth, and then the surface of the Earth is my S2. Gotcha.
And if you wish, you can even think of this as completely empty. So you could think of it as no center, which is sort of a type of hole, I guess.
Okay.
Which might, well, we'll see what happens. Okay. So now the question is, you can add a base point anywhere you like on your sphere, and then you can draw any loop that you like from your base point. That's a great base point.
Yeah, I picked the North Pole. And
North Pole,
let's say I drew like let's just draw something coming down and going back like that.
Okay, I agree. So can you draw, I'll ask us the same question. Can you draw a different loop that is not homotopy equivalent to the loop you just drew?
Okay, so is there something I can interlock with? So even though you've said it's hollow, I'm guessing... I don't think the fact that it's hollow necessarily, at least in my head, corresponds to it having a hole. Because I can't get anything through that hole.
That's right.
If I'm on the outside surface, I need to puncture. I need to puncture the sphere to drop inside and then puncture to come back out or something. So I don't think I can. I think whatever I were to do, I go down to the South Pole, maybe come up the back. Whatever I do, it can still be shrunk to that single point, I think.
I completely agree. Yeah, even those big equatorial ones, you can just think of, okay, nope, I just shrink it all up to a point.
Yeah.
Okay, so let's call this one 0 as well.
Yeah.
Oh, I wonder whether I should give you another 0, 1, just to keep on tempting you.
I was about to say, they're not all 0. Is this the big trick?
It would be quite a silly theory if that was the case. The fundamental group gives that every space is 0. Okay.
Yeah.
Now, I gave you the two-dimensional one. Now I'm going to give you the one-dimensional one. So S1, which is the circle, but just the line living in the plane.
Okay, so now just an actual circle.
All right, so you can put your base point, say your North Pole on this once again, if you so choose. How do you draw a loop that lives in S1?
Now, I could draw something like so.
Ah, but you violated your condition. I maybe wasn't precise of what I mean by S1. By S1, I mean...
it has to go along the circle.
That's right. Only the outside surface. No inside. So you can't draw on the inside at all. That's illegal.
Can I go outside of it at all?
Not at all.
So I can only go along the line.
Previously, it was like we were walking on the surface of the Earth. Now we're just imagining we're down a dimension. We're walking just like that. So you could do a loop that way.
That's all we can do.
Okay.
Right. But that would be it. So I couldn't go along and then turn around and come back?
Well, you could. That would be a valid loop. It would be equivalent to just staying put, though.
Yes.
Right, so the loop that goes out a little bit and comes back is a loop. It starts at the base point and it ends at the base point, but it could just be contracted right back to the base point. That would be equivalent to the element 0.
Yeah, I see.
Okay, so you've got a 0, which is anything that doesn't loop around. You drew 1, which is loops all the way around.
Yeah.
Can you draw a loop that's different from either of those?
But I'm not allowed to leave this line.
That's correct.
Could I
You can
wrap
repeat
around
you can go on top of yourself if you so choose.
Oh, could I go round it twice?
You go around twice. You could go around the opposite direction.
Yeah, of course. So I've drawn, I guess originally I've drawn that one, but then I could, of course, if I just draw it on the outside to emphasize, go around like that, couldn't I? Yeah, in the other direction.
That's right. So I think when I look this, I could loop around no times, 1 time, 2 times, 3 times, 4 times, -1 times, -2 times, -3 times, and so forth.
Any integer number, I think.
That's right. So let's call pi1 of s the integers.
I see. Nice.
Right.
Yeah.
So now we have a group that that's one of the first group that everyone learns about, even when they don't know that it is a group. The integers under addition.
Yeah. Of course.
So we have a clearer association between an algebraic object, the integers, and this very sort of, topological object, these loops inside of here. And it's sort of interesting to me that because we're doing pi1, which is maps from the S1, the circle, into spaces, it didn't see the two-dimensional hole inside the surface of the Earth. It sort of, it wasn't the right dimensionality of hole. Pi1 finds holes that are sort of in one dimension in some sense. Okay, I'm going to give you your last one of the day, and then we'll do a cute little theorem. Okay, I don't know how well you are at drawing a donut. I'm going to draw a donut for you down here. You can copy it if you so wish. This is my normal way of drawing a donut.
Okay.
Looks something like that.
You drew it like that, and then you kind of did an upward one, and something like that. Okay.
Yeah,
cool.
you can sort of visualize your donut, and we can put our base point wherever we so choose somewhere. Exactly. Yeah, that's nice. So a nice way to do it. It's sort of a circle, and I have my son's playdoh, which I'll say is the same, and we have the cup, which we all think of as the same thing, right? These are all sort of topologically the same. Okay. So our goal is to figure out the fundamental group of this object. Okay. So, why don't you just tell me about a few paths that you can imagine? Well, if you have your base point there, what are some paths that you could potentially do?
So I'm thinking that one.
Yep, goes all the way around that central hole. Good.
Yeah, going around the central hole. I'm thinking I can loop through the middle and underneath and back up.
Yep.
That way. That's definitely a different one.
Mm-hmm.
I guess I could continue to loop around as I go around,
right.
All the way like this.
Yep.
Would that be something different, or would that?
Yeah, I think so. It's kind of like how the previous one we had like 1, 2, 3 loops around.
How many times? I see.
Yep.
So what we're going to get here then is so we can loop this one around in one dimension, so I can go like that, but then I could do it plus or minus.
That's right.
So that's kind of giving me Z.
Yep.
From the outside bit, but then I can do the exact same here around that central hole, continue to go round or change the direction. So I'm getting like Z cross Z.
That's exactly right. Yeah, so pi1 of the what we call this 2 torus here is Z cross Z.
Yeah, brilliant.
And really there's just no other way that you can loop, but you can loop any combinations. 3 times the one and twice the other way, and any combination thereof.
3. Yeah, so you kind of go around to get back to where you started and then do 2. Yeah, I see. Yeah.
Okay, delightful. So, as you can imagine, we could then go on. We're not going to do more now, but we could go and compute what the fundamental group of many different spaces was, and we could, if we were confused and they were complicated, you and I couldn't quite tell the difference between them, if we got a different fundamental group, we would now have learned something, that these spaces were meaningfully different in this appropriate sense. So, I'm going to finish with one application that we can actually really learn something from, and this is the classic theorem of Brouwer. This is Brouwer's fixed point theorem, okay? And, I mean, you'll have probably seen this in many different contexts. If you know complex analysis, it comes out of there, for example. This is a classic theorem that can be proved many, many ways, but we're going to be able to almost trivially prove it, at least if you believe all the machinery of the fundamental group, and we've just done it intuitively, I haven't done the proofs, and if you believe that machinery, then we can get the theorem. Okay, so what does the theorem say? Well, there's a couple different interpretations of Brouwer's fixed point theorem, but imagine you've got the foam on the top of a cup of coffee, and the top of a cup of coffee is kind of like a two-dimensional disc, if you will, and you mix that foam. The claim is there is some spot in that cup of coffee, on the foam on the top of the cup of coffee, that is exactly where it began. So if you just rotate everything around, the midpoint would be the spot where it was fixed. But no matter, the theorem is no matter how crazy, like you just go nuts and just like stir as quell, as long as you're just doing a transformation of that two-dimensional plane and that it's continuous, there's always this fixed point, the spot where f of x is just equal to x.
Is this similar to the idea that at some point on the Earth, somewhere else has the same temperature and pressure as one other point?
The theorem you're citing is Borshak-Ulam. They're very similar. They can both be proven, but they are slightly different statements. And actually, I have a video on Borshak-Ulam that you've given me the opportunity to plug. It's a great theorem.
That was just what came to mind. I was just thinking. I really like your coffee cup example. It just reminded me of a similar. I guess
it is very similar indeed. It's a fixed point theorem that proves Borshak-Ulam theorem. You're absolutely right.
Right.
Another one I really like. Okay, take two maps, identical pieces of paper, the identical map. You lay one map down and you scrumple up the top map, but you don't tear it. It has to be continuous. If you then put the scrumpled map on top of the flat map, there's always one spot exactly over top of where you started. Yeah. So it might be Oxford, but it might be any other place, right? So there's always that one fixed point where the f of x, your function is like the crumpling function, where f of x is just actually equal to x.
Yeah.
Okay, so let's see how we could prove a claim that such as this. I'm going to assume that it's false. Our classic proof by contradiction. And the way I'm going to do this is I assume that it's false. This is the same thing as saying that f of x is not ever equal to x. So it doesn't matter what x it is, f of x is never equal to x. So that means if I put a point x here, I can always come along here and have my point, not the partial derivative, f of x. Like we always have that sort of distinction there.
Yeah.
And because we have that distinction, I can do the following. I can draw a little ray that goes from f of x through fx and ends up right there, and I'm going to call that point r of x. Okay? So this basically says I have this new function, the endpoint of this ray, and as long as this assumption is false, you can get to this point which is on top of your circle. Okay, now, we know that the disk, which is basically the same thing as R2, if you consider the whole disk, that we know what its fundamental group is, right? It was 0, like you could contract everything down. Like for example, if I had drawn a loop that went around the boundary, I could sort of do a homotopy and contract it down to there, and contract it down to there, and contract it down, and I could just send it all the way down. I could loop it through if I had a middle.
Yep.
So, in other words, what I'm going to have here is I have ft, and this is going to be a homotopy that's going to take any boundary loop and sort of put it right down into the middle. Okay?
Okay. Yeah.
So if I let, here I'll denote it in pink, I'll let f0 be on S1. In other words, this is the path that just goes around like it's a single loop around the outside edge, right? It's restraining itself to the boundary of the circle, but it has this homotopy that sort of goes through the circle in some sense. Okay, so let's think about the following. RFT. And try to understand what R of ft does. So basically, ft is all these things that go through the middle, you know, depending on the t value, it's somewhere in the middle of the disk. Mm-hmm. But because of the R was the thing that follows the ray and goes to the boundary. So RFT is going to end up with a point on S1. As in all of these points here, this is going to be a map that ends up entirely, it lives in the S1. It lives on the boundary, not in the center. The sort of the FT that we had here was a homotopy that went through the center, but it's sort of it's a middle move, right? The output after you also have the R, the composition with R, ends up on the S1. Okay, so this is a homotopy. Is a homotopy from the original F0 that goes around the boundary to just x naught, the constant map that just stays at your base point and never moves at all. Yeah. In other words, what we've said is any loop that is around the boundary can be contracted just to the constant. And this is a contradiction. Right, we had that pi1 of S1 here was not equal to 0, but we've just shown that indeed it must be the case that any loop, if you had this property, could be contracted. And this contradiction means our assumption is false, and so the claim that f of x is not equal to x is false, and thus proves our little theorem.
So am I right in thinking that the key thing there was because you have this x and an f of x somewhere, you can then get, drawing a line through those points gives you this point or this map R that takes you to the edge.
Exactly.
That's kind of like the key thing. Whereas if those 2 points were the same, then you don't know where R is.
Yeah, you'd have no way of defining where your ray was supposed to go to, right?
Because you've just got 1 point and you can just draw any ray you want, but if you've got 2 points, you can only draw a specific ray.
That's right. So basically, because of the existence of that R that we just talked about, now you can make this RF, this funky way that you can contract everything, but you know you can't contract everything, and hence we've proven our theorem.
So obviously R can't exist in the first place, therefore X and Fx have to be the same point, so therefore you couldn't define R. Gotcha, nice. Yeah.
So that is our little theorem that we can see. We're not just drawing pretty diagrams and associating, integers to them or integers cross the integers. We can actually use that tool if we believe all the machinery that does need to be fleshed out. But if we believe all that machinery, then indeed we can actually prove something kind of non-trivial. And in fact, many non-trivial things from this. So that's my introduction to algebraic topology. Have I convinced you to come to the dark side?
I honestly loved it. I particularly the thing I felt as though the way you set it up, and when I was doing that Torus question in particular, I genuinely felt really happy that I'd able to spot the Z cross Z thing. Honestly, just because initially I think with the circle idea, I sort of had perhaps with some of your help obviously figured out roughly that we had all these different values, but then as soon as you mentioned Z, and then I was sort of very pleased with myself, let's say, when I spotted on the Torus, so you could get Z cross Z this time because there's 2 different loops.
Oh, I'm so glad. Yeah, I was hoping I wasn't going to have to help you on that one. I didn't have to help you at all, and I was super happy about it.
No, I found that. No, that was brilliant. I had that sense of achievement and wonder that you get when doing new maths, and so for that alone, I loved it.
Okay, we share the sentiment on our respective videos then. Okay, very nice. All right, Tom, I very much enjoyed you coming onto my channel. Thank you so much for being here.
Genuinely an absolute pleasure. Thank you so much for having me and for being such an awesome teacher and giving me that sense of wonder, which is why we all do maths. I loved it.
Oh, I'm so glad. And for any of the viewers, if you have any questions, do leave them down in the comments below. Check out Tom's video that we recorded on fluid dynamics. It's really cool. I'll put the link to his channel, and we'll do some more math in the next one.